Hello everyone, I am Faranjam from Sri Venkateshwara College of Engineering, Bangalore. The topic for today's presentation is Ground Level LiDAR as a contributing indicator in an environmental protection application from the course Environmental Protection and Management. Abstract. The value of forests in developed countries has evolved from focusing primarily on commercial wood production to emphasizing carbon reduction, wildlife habitat, aesthetics, and recreational opportunities. This shift has led to increased concern for forest management and the development of various research initiatives that leverage advanced technologies to monitor forest health, wildlife, and incidents such as fires and illegal activities. The paper introduces an expert system designed for forest environmental protection, which incorporates remote sensing hubs and a central cloud server. It highlights the innovative use of ground-level laser imaging detection and ranging (LiDAR) and sensors to gather valuable data about forests' environments. The paper also discusses the implementation details and presents test results from the forest setting. Introduction. Forest exploitation has existed since early human tool development, but with rising global populations, sustainable and responsible logging practices have become increasingly important. The vastness of forest areas makes it challenging to monitor and protect them from illegal activities and environmental threats. Recent technological innovations provide opportunities for improved environmental monitoring, including systems like infrared thermal cameras, LiDAR, and synthetic aperture radar to detect fires and illegal logging. The authors developed and tested an expert system for forest environmental protection, focusing on ground-level LiDAR sensors to collect data and integrate it with signals from other sensors to identify threats in the forest. The paper outlines the system prototype, its architecture, and testing in real forest environments, discussing challenges encountered and proposing avenues for future research. Related work. Researchers have developed a conceptual wireless sensor network aimed at preventing illegal deforestation through acoustic signal evaluation and node communication, focusing on low energy consumption and reliability, but it has not yet been tested in real-world conditions. The Forest Guardian system detects sounds related to deforestation activities and sends instant notifications to responsible parties. Its modular architecture allows for the addition of new functionalities, and it includes a web application for monitoring at-risk areas. Small drones are increasingly utilized by timber companies and NGOs for forest management tasks, including mapping, pest monitoring, and surveillance against illegal activities. While drones offer high spatial resolution and cost effectiveness, they also face challenges such as sensitivity to weather conditions and potential safety issues. Experimental model. Sensing hub hardware. A long-range LiDAR sensor is mounted on a rotating platform powered by a stepper motor, chosen for its precise control and operational advantages such as being brushless and maintaining fixed speed under varying loads as shown in the figure. The unipolar stepper motor allows for high resolution in movement due to its design, which can include multiple rotor bolts, enhancing the precision of angular displacements during operation. The system incorporates specialized integrated circuits for efficient motor control with features like freewheeling diodes to prevent damage from transient currents, ensuring synchronized and stable rotor operation during dynamic conditions. Sensing Hub software. The Python code for the Raspberry Pi was split into multiple script files, each file dealing with one aspect of data gathering process as shown in the figure. Getting data from the LiDAR sensor, controlling the motor, getting data from the particular PMS5003 sensor, getting data from the Pimoroni Enviro Plus sensor, logging the data, and the main script. Central Server Backend Software Stack. The dashboard for interacting with the system is built using the LAMP stack, Linux, Apache, MySQL, PHP, offering a secure, scalable, and customizable platform for fast development. Various PHP frameworks were considered, including Laravel, Symfony, Code Igniter, Cake PHP, Falcon, and YII, each offering different strengths like ease of use, flexibility, performance, and community support. Based on the needs of the project, including scale, security, development time, and resources, Laravel was chosen as the most suitable framework due to its simplicity, flexibility, and extensive developer community. Central Server Front-End Software Stack. The web app enables remote devices to send gathered data to the server via an API, while registered users can inspect data from multiple devices and manage their accounts, including registration and access control. Users can have different access levels, registered, active, or admin, affecting their ability to interact with data and perform actions like adding or managing devices, with each device having a unique serial number for validating data submissions. To address connectivity issues, the app allows manual data uploads and stores sensors readings locally as a backup, ensuring no data loss occur during server downtime and facilitating continuous data monitoring when connections are restored, as shown in these figures. Experiments. A remote sensing hub was installed near a forest in Romania to assess the expert system effectiveness. Early issues included tension in the LiDAR, connection cable causing motor misalignment and drift during rotations, which was partially resolved by replacing the cable with a lighter one. Overlapping connections between the motor and the particle sensor initially prevented simultaneous readings. This was resolved by connecting the LiDAR through a serial USB port, allowing the particle sensor to use the RT or TX pins. The LiDAR sensor's resolution was sufficient at longer distances, making detailed readings difficult. Sequentially, movement and reading operations were made for consistency, ensuring fixed readings for better comparison between runs. The LiDAR could not accurately read through glass due to reflections, and glass surfaces in the environment posed challenges. However, it successfully detected foreign objects placed between the hub and trees, triggering alerts in the system. Initial visualization of all LiDAR records slowed down the web interface. The code was updated to allow section-wise data loading, improving performance and user experience while inspecting the 3D surface plots of the recorded data. Conclusion. The proposed IoT-based systems used LiDAR for real-time forest monitoring, detecting foreign objects and environmental changes like smoke or fog, and sending alerts to users. It has proven effective in critical situations, improving safety and response times. However, it faces challenges like sensor drift and false positives from wildlife or weather conditions. Future research aims to enhance accuracy with self-correction mechanisms, classification algorithms, and integration with other sensing technologies, expanding its applicability in various domains. These are the references of the research paper. Thank you for watching the video.